Good morning, everyone. Welcome back. It's good to have you. Thank you for joining us. I'm Steve,
And I'm Scott.
and together we're Backyard Musings, Science and Technology channel.
Yep, and we're talking about probably one of our most favorite, if not our favorite, space telescope today, James Webb Space Telescope.
And so,
there's a picture of it.
what you see on your screen is the James Webb Space Telescope. It's pretty amazing. It's like an array that sends signals, an antenna array. And it's like we said yesterday, 1.5 million miles away from the Earth, orbiting the sun. It's pretty cool.
That is cool.
It's like Star Trek science fiction stuff.
Yeah. Now, we were talking just before we went on, and I had thought I was mistaking it for the James Webb. I'm sorry, the Hubble telescope. Hubble telescope, and it's a little bit more.
That's in orbit around the Earth.
Yeah, and that looks more like a normal
round
telescope.
Cylindrical. Yeah.
This thing is cool.
Yeah, it is. It's like
Star Wars.
Yeah. A sizzling exoplanet caught by the James Webb Space Telescope is shedding its atmosphere and leaving behind two gigantic helium trails. Astronomers from the University of Geneva, the National Centre of Competence in Research Planets, and the Trottier Institute for Research on Exoplanets at the University of Montreal have made an unprecedented discovery with the James Webb Space Telescope. For the first time, scientists were able to observe gas escaping from an exoplanet's atmosphere continuously over an entire orbit around its star. Would you like to know more?
Well, I don't exactly know how to fathom that, but it sounds pretty cool. So, the observations revealed a striking and unexpected sight. The gas giant WASP 12 or 121b, that's WASP 121b, is surrounded by two enormous streams of helium that stretch across more than half of its orbit. When combined with detailed numerical models developed at UNIGE, again, I don't know what that stands for. Maybe that stands for that school. Oh, that's
the school, yeah.
Okay. It says University of Montreal. I don't know. Anyway.
Way up at the top.
Yeah.
Geneva.
The data provide the most complete picture ever assembled of atmospheric escape, a process that can dramatically reshape a planet over time. The findings are published in Nature Communications on December 8th, 2025.
Now, this WASP, that sounds familiar. WASP 121b means it's the second planet from the star. But WASP 121 really sounds familiar.
Like we talked about a WASP before, you mean?
Yeah, I think so.
Could be. Yeah.
Okay, WASP 121b belongs to a group of planets known as ultra-hot Jupiters. Yeah, we talked about the big Jupiter planets. Yeah. These massive gas giants orbit extremely close to their stars, and WASP 121b completes one full orbit in just 30 hours. It must be really close. Its nearby star bombards the planet with intense radiation, heating the atmosphere to several thousand degrees.
At these temperatures, lighter elements such as hydrogen and helium can escape the planet's gravitational pull and drift into space. Over millions of years, this steady loss of gas can significantly alter the planet's size, chemical makeup, and long-term development.
Before this study, scientists could only capture short snapshots of atmospheric escape during planetary transits, the brief periods when a planet passes directly in front of its star. These limited observations lasted only a few hours and offered an incomplete view of how atmospheric flows behave. Without continuous coverage, researchers could not determine how far the escaping gases extended or how their structure changed throughout the planet's orbit.
To overcome this limitation, astronomers used the near-infrared spectrograph, NIRISS, or NIRISS for short, aboard the James Webb Space Telescope to observe the WASP 121b for nearly 37 uninterrupted hours. This observation covered more than one complete orbit, making it the most extensive continuous study of helium ever conducted on a planet. The prolonged monitoring allowed scientists to track atmospheric escape in unprecedented detail.
By
Interesting.
measuring how helium absorbs infrared light, the team discovered that gas surrounding WASP 121b extends far beyond the planet itself. The helium signal remains detectable for more than half of the planet's orbit, representing the longest continuous detection of atmospheric escape ever recorded.
Even more surprising, the helium forms two separate tails. One trails behind the planet, pushed backward by radiation and stellar winds. The other curves ahead of the planet, likely drawn forward by the star's gravitational pull. Together, these flowing structures span a distance exceeding 100 times the planet's diameter, or more than 3 times the distance between the planet and its star.
Wow. Quote, "We are incredibly surprised to see how long the helium escape lasted," explains Romain Allert, a postdoctoral researcher at the University of Montreal, former doctoral student at the University of Geneva, and lead author of the paper. Continue to quote, "This discovery reveals the complexity of the physical processes that sculpt exoplanetary atmospheres and their interaction with their stellar environment. We're only beginning to discover the true complexity of these worlds."
The Department of Astronomy at the University of Geneva has long played a leading role in atmospheric escape research. Numerical models developed there were essential for interpreting the first helium observations made with the JWST, or the Space Telescope.
While these models can successfully describe simple comet-like gas tails, they struggle to recreate the double-tailed structure seen around WASP 121b. Quote, "This discovery indicates that the structure of these flows results from both gravity and stellar winds, making a new generation of 3D sims essential for analyzing their physics," explains Jan Carteret, a doctoral student in the Department of Astronomy at the Faculty of Science of University of Geneva and co-author of the study.
Helium has emerged as one of the most powerful tools for tracking atmospheric escape, and the James Webb Space Telescope sensitivity now allows scientists to detect it over greater distances and longer time periods than ever before. Upcoming observations will help determine whether the double-tailed structure seen around WASP 121b is unusual or common among hot exoplanets.
Researchers will also need to refine existing theories to better explain how gravity, radiation, and stellar winds work together to shape escaping atmospheres. Quote, "Very often, new observations reveal the limitations of our numerical models and push us to explore new physical mechanisms to further our understanding of these distant worlds," concludes Vincent Boyer, lecturer and researcher in the Department of Astronomy at the Faculty of Science at the University of Geneva and co-author of the study. Fascinating.
Yeah, we love anything that is connected with the James Webb Space Telescope. And now that we've actually seen a picture of it, or I have, I'm even more fascinated. It's just very cool.
Back up there. I'll throw it back up there.
Put that together. That just,
it's amazing. Before the show, Scott and I were talking about, does it move? It has to move because I don't think there was a space barge that towed it out there, so it had to have some thrusters. And then if they need to realign, they got to put some thrusters on to realign. So I think it can move.
Yeah, to keep it safe out there, right? It almost looks like a centerpiece for a table. It's pretty cool.
It is really cool.
Yeah.
All right, folks. Thanks for joining us, and we'll talk to you this afternoon.
Take care, everyone. We'll see you this afternoon.